Alright, let's go ahead and do our second video on the integral tests and corollary, the P-series test. Let's go ahead and just jump right in. Let's do 1 over n natural log of n. Now, why is this 2 to infinity? Well, because if it's natural log 1, then you basically have a 0 in the denominator. Okay? So what we need to do now is we need to evaluate 2 to infinity of 1 over x square root of the natural log of x dx. Okay? Well, that ought to be easy enough. We know that this is likely going to be u sub. And so let's go ahead and just set it up like that. We'll go ahead and put it in the limit notation. It goes 2 to b of natural log x to the negative 1/2 times 1 over x dx. So that's u to the negative 1/2 du. So we have the limit as b approaches infinity, and u to the negative 1/2 becomes u to the 1/2 over 1/2, or 2 root u, right? So we have 2 root u from 2 to b, and so that's the limit as b approaches infinity of 2 natural log b minus 2 root natural log 2. And despite the fact that this goes to infinity rather slowly, it still goes to infinity. That is infinite, or according to some teachers, does not exist, and therefore we recognize this as divergent, and because it's divergent, the original series that it's related to is also divergent. Okay, another example. How about sigma n is equal to 1 to infinity of n over n to the 4th plus 1. Well, that means that 1 to infinity of x over x to the 4th plus 1 dx is basically the improper integral that needs to be evaluated in order to determine what's going on, in order to determine the convergence or divergence of the original series. Now, it probably will help a little bit, again, limit notation, 1 to b, if I go ahead and write this denominator as x squared squared plus 1. Okay, that means that I'm going to need, in addition to my 1/2 up there, a 2 and a 1/2 to go along with it, right? This groups together with my dx to be my du, and this winds up being arctan. Okay, so let's pull the 1/2 all the way out in front because, you know, I can. And this winds up being arctan x squared from 1 to b, and then we just simply need to evaluate it. So we have 1/2, the limit as b goes to infinity of arctan b squared minus arctan of 1 squared, or just arctan of 1. Now remember that arctan has an output boundary, that asymptote at pi over 2. What that means is that when you square the input, you're just making it approach that, you're not changing that asymptote, you're not changing the outputs, you're just changing the rate at which the inputs approach that output. Well, it's going to infinity, so that really doesn't matter all that much. And so what I get here is I get pi over 2 minus pi over 4, or 1/2 times pi over 4, which is pi over 8. It doesn't really matter what the actual value is, just that it is a finite recognizable value. And therefore I know that this converges at pi over 8. Therefore this converges, probably somewhere close to pi over 8. But remember, this is functionally the infinite Riemann sum for this, so the answers are going to be just a little bit different. Okay, well, how different? Well, I happen to know, and the book actually tells me, and 34 and 35 wind up being pretty neat problems because they wind up talking about Leonhard Euler and his proof of the fact that 1 plus 1/4 plus 1/9 plus 1/25 plus dot 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 actually turns out to be pi squared over 6. Okay, it's a very famous proof that he did, and you can actually Google it and look it up on YouTube. Once we're done with this chapter, you'll actually be able to understand the proof just fine. Now, that of course that means that sigma n is equal to 1 to infinity of 1 over n squared is pi squared over 6. He also figured out that from 1 to infinity of 1 over n to the 4th is pi to the 4th over 90. Okay? But what we're going to do is let's go ahead and find the partial sum to 10 decimal places. Okay? So we're going to estimate n is equal to 1 to infinity of 1 over n to the 4th by my partial sum at 10, which is n is equal to 1 to 10 of 1 over n to the 4th. Now, if you actually plug that into your calculator, which I've taken the liberty of doing before I started the video, it's approximately 1.082 on and on and on and on and on and on and on. Okay? Well, here's the thing. We have an error formula in the book which actually tells us, and it has to do with that relationship between the integral and the Riemann sum. The fact that the Riemann sum can help us estimate the integral, the area under the curve, that also means that the area under the curve can help us estimate the Riemann sum, meaning the series, okay? And because of that, and it lays that out from 718 to 719, I know that there's this general formula that says that the nth partial sum plus the integral from n plus 1 to infinity and the nth partial sum plus n to infinity of f of x dx. Now these are going to be very, very similar, right? Because this is the partial sum and this is the interval. So basically for this particular one, this would be s sub 10 and the improper integral from 10 to infinity of 1 over x to the 4th. And this is s sub 10 plus the integral from 11 to infinity of 1 over x to the 4th. Now those values actually sandwich, they squeeze, or they basically provide boundaries for the actual value, okay? And if you want to see how that's set up and how that's established in terms of all the notation and stuff like that, that's the last couple of pages of your book in 11.3. I'm just going to show you basically the import here. Now, all I need to know, since I'm going to be integrating for n to infinity and n plus 1 to infinity, why don't I just go ahead and find myself the general form for n to infinity of 1 over, x to the 4th dx. Because I can do that, okay? And once I've done that, it actually winds up being 1 over 3n cubed, okay? So that basically means that if I go from 10 to infinity of 1 over x to the 4th, that n gets substituted in here, and I get 1 over 3 times 10 cubed, okay? And if I wind up doing 11 to infinity of 1 over x to the 4th, that's 1 over 3 times 11 cubed. And I could do the actual integration for you, but you're just as good at doing it as I am. It basically winds up just being the same process of improper integration, just in the abstract with an n here instead of an actual value. And so it doesn't spit out a number, it spits out an expression in terms of n, and that would be it. So what this really means is that the s sub 10, the approximation, plus 1 over 3, 11 cubed, and then the approximation plus 1 over 3 times 10 cubed, those sandwich the actual value. And of course, 1.08 is an approximation. When you do it with your calculator, store it into A or whatever, and actually keep the actual value in your calculator. Because once you actually evaluate this, it winds up giving you 1.082287,021. And once you actually evaluate this, it winds up giving you 1.082369916. And those are the boundaries for what the actual sum is. And we'll compare it here in just a minute. Now, what is the error? Okay. Well, obviously this is the interval, and the error is going to be roughly half that. Okay. And the error winds up being, to like 5 decimals or something like that. Let's actually see whether the actual value of pi to the 4th over 90 winds up being in between those two values. By the way, it does. Pi raised to the 4th over 90, press enter, and we get 1.0823, so it's already larger than this one, 2, so it's smaller than this one. And that actually winds up being smack dab right in the middle of those two boundaries. Okay? And so all we're doing is we're using the estimate and two separate integrals, two separate improper integrals, to sort of sandwich in and give us an idea of exactly where the actual value is and how good of an approximation S sub 10, the 10th partial sum, actually is for the actual value. And they would occasionally do stuff like this, and they would use errors and bounds because they didn't always know exactly what the value was. In fact, the one that we were discussing earlier, which is 1 plus 1/4 plus 1/9 plus that, the n is equal to 1 to infinity of 1 over n squared. It took a while for them to figure out what it was, and in fact one of the Bernoullis posed the question, and he wound up getting a very, very good approximation for it before Euler finally figured it out, and then of course got the actual value for it. So before they knew the actual value, because they actually needed a representation of what it was, they actually were able to estimate it. And that's one of the reasons why you're learning all of these approximation methods, not only because they're helpful in terms of understanding kind of ranges and errors and stuff like that, but it gives us an idea of sort of the historical emergence of some of these values, of some of these methods, and really kind of the hard work that a lot of these mathematicians put in order to arrive at some of these just absolutely majestic formulations. I mean, this is actually considered, the fact that he actually figured this out and told us that it was, pi squared over 6, is one of the most famous proofs in the history of math. And it's a staggering feat, and I hope that at some point you'll look it up online and actually take a look at that, because it really is kind of neat. This is it for integral test and P series. I hope that winds up being rather clear. We'll move on in the next one to comparison and limit comparison, and I've already sort of mentioned comparison test. We'll go ahead and move on to that in the next video. We'll probably do 2 videos on that particular section, and from there, after comparison and limit comparison, we'll get into alternating series, which are the series that go plus minus, plus minus, plus minus, plus minus, and those are kind of fun as well. So any questions, please do email me, and I will do my best to provide clarification. Bye.